Before we continue, subscribe to Sports Science Insight. Here, we break down new sports science research and translate the findings into practical information for athletes, coaches, and practitioners. In this video, we examine the article titled, Stroboscopic Training Effects on Athletic Performance and Cognitive Function Across Populations, Purposes, and Skill Types. The systematic review and meta-analysis was conducted by Jintao Guo and colleagues and published in Frontiers in Sports and Active Living. The central question is simple. Do stroboscopic glasses actually improve athletic performance, or do they only make training look more advanced? The answer is promising, but also more selective and context-dependent than the marketing around these devices may suggest. Let us look at the evidence. Stroboscopic glasses use liquid crystal lenses that repeatedly alternate between transparent and opaque states. This does not completely eliminate vision. Instead, it provides visual information in short, intermittent samples. Imagine trying to track a ball when you can only see part of its trajectory. The brain must predict what happens during the missing visual intervals. The athlete may also increase reliance on proprioceptive and vestibular information to maintain movement control. The intended adaptation is not simply to tolerate visual difficulty. It is to improve how efficiently the athlete uses limited visual information. This may strengthen predictive control, anticipatory timing, and the integration between perception and movement. But does this process produce measurable benefits? To answer that question, the researchers conducted a systematic review following PRISMA guidelines. They searched PubMed, Web of Science, Sport Discus, and the Cochrane Library through August 2025. Only randomized controlled trials published in English were included. 14 studies met the eligibility criteria. 8 evaluated cognitive outcomes, and 8 evaluated athletic performance. Some studies contributed outcomes to both analyses. The studies included volleyball and football players, healthy participants, and individuals with chronic ankle instability. The interventions ranged from isolated visual tasks to sport-specific exercises, balance training, ball control activities, and rehabilitation protocols. Most interventions lasted between 4 and 6 weeks and were performed approximately 3 times per week. This diversity allowed the researchers to examine several applications, but it also contributed to considerable variation between studies. The overall results were positive. For cognitive function, stroboscopic training produced a standardized mean difference of 0.64. For athletic performance, the standardized mean difference was 0.58. Both represent moderate average effects in favor of stroboscopic training. However, these values should not be interpreted as percentages. A standardized mean difference expresses the distance between groups relative to the variability of the measurements. There was also substantial heterogeneity. The I-squared value was 81% for cognitive outcomes and 64% for athletic performance. This means that the average effects were positive, but the results varied considerably according to the participants, tasks, protocols, and measurements. The next question is therefore essential. Which abilities actually improved? The cognitive findings were not uniform. Stroboscopic training produced a standardized mean difference of 0.75 for perceptual ability. The effect on information processing speed was also 0.75. Both results were statistically significant. Attention, however, showed a much smaller effect of 0.22, and this result was not statistically significant. This distinction is extremely important. The evidence does not support the broad claim that stroboscopic training improves cognition in general. Instead, the benefits appear to be concentrated in abilities associated with detecting visual information, processing movement, anticipating actions, and coordinating perception with motor responses. In practical terms, athletes may become better at using visual information quickly without necessarily improving general attention. And the participants' previous training status also appeared to matter. The subgroup analysis revealed a clear difference between athletes and non-athletes. Among athletes, the standardized mean difference was 0.89. Among non-athletes, it was only 0.23. This difference was statistically significant. One possible explanation is that trained athletes already possess well-developed perceptual and motor abilities. Stroboscopic training may build upon this existing foundation, helping the athlete refine established skills rather than creating completely new abilities. An experienced player already understands relevant movement patterns, visual cues, and tactical situations. The visual restriction may encourage that player to use these existing resources more efficiently. For a non-athlete without the same perceptual motor foundation, the same visual challenge may provide a much smaller benefit. This leads to an important practical principle: the training task should remain closely connected to the actual sport. The findings suggest that stroboscopic training may be more useful when it is integrated into meaningful sport-specific activities. The included studies used exercises involving volleyball, football, ball control, reactive movement, balance, and rehabilitation. This is important because improvements in an isolated visual task do not automatically transfer to competition. For transfer to occur, the athlete must connect visual processing with the movements, decisions, timing, and environmental demands of the sport. For a volleyball player, this might involve reading the setter, tracking the ball, or preparing to block. For a football player, it might involve receiving the ball, scanning the environment, or making a decision under pressure. The glasses should add a controlled visual challenge to the skill. They should not replace technical, tactical, or physical training. The duration of exposure may also influence the results. The meta-regression showed that greater total intervention duration was associated with larger effects for both cognitive function and athletic performance. Based on their synthesis, the authors proposed protocols lasting 6 to 10 weeks, with 2 to 3 sessions per week and approximately 10 to 20 minutes per session. This is a useful starting point, but it should not be treated as a definitive prescription. Most of the included trials lasted between 4 and 8 weeks, and several used sessions lasting 20 to 30 minutes. The analysis identified an association between accumulated training time and effect size. It did not directly compare every possible combination of frequency, session duration, and training intensity. We therefore cannot say that one exact protocol is optimal for every athlete or rehabilitation patient. The difficulty should also be progressed carefully. Excessive visual restriction may reduce movement quality and turn a training stimulus into an unnecessary obstacle. But why might repeated exposure produce these adaptations? One proposed explanation is sensory reweighting. Human movement depends on the integration of visual, proprioceptive, and vestibular information. When visual information becomes intermittent, the nervous system may dynamically adjust how much it relies on each source. The athlete must use the available visual samples more efficiently while also increasing reliance on body position, balance information, and movement prediction. Over repeated sessions, this process may strengthen the neural pathways involved in visuomotor timing and anticipatory control. The important point is that this is a targeted adaptation. The findings support improvements in perceptual motor integration, not a general enhancement of every cognitive function. The proposed mechanisms are plausible and supported by related neurophysiological research, but the meta-analysis does not directly prove one single neural mechanism. This brings us to the practical conclusion. Overall, stroboscopic training produced moderate average benefits for cognitive function and athletic performance. The cognitive improvements were selective, with stronger effects for perceptual ability and information processing speed than for attention. Athletes appeared to benefit more than non-athletes, supporting the use of this method within established sport-specific training. However, the evidence also has important limitations. The studies used different protocols and outcome measures. Participant blinding was impossible, publication bias was detected, and most interventions were relatively short. We still need better evidence about long-term retention and whether laboratory improvements consistently transfer to real competition. The practical message is balanced. Stroboscopic glasses can be a promising supplementary tool, especially for trained athletes performing relevant sport-specific tasks. But they should not replace technical practice, tactical learning, physical preparation, or qualified coaching. If this video helped you understand the evidence, leave a like, subscribe to Sports Science Insight, and follow the channel for more research-based sports science content.